Hello and welcome to the quest for a magic square of perfect squares of size 3. As you probably know, it's an unsolved problem at the present day because no one could find a solution and no one could either prove that there's no solution. So I'd like to show you my way of seeing this problem. So first we'll start with definitions and examples, and then I want to show you a parametrization of the problem. Then, because it doesn't work, unfortunately, I would like to show you a more advanced parametrization and then focus on a specific example. At the end, the outcome of this would be what could happen in the future. So let's start with some examples, basically where we're at. So we're looking for a magic square. What is that? It is a square of size 3 by 3, which contains integer numbers, all different, relatively prime, and in that square, all of the rows, all of the columns, and both diagonals add up to the same number, 72. Joke aside, it's not always 72, but it's a constant for that square, and we call it the magic constant. According to the title, we're looking for a magic square of perfect squares. So our square contains perfect integer squares, and all of the rows, columns, and diagonals add up to the same number. Let's take a look at some famous examples, and probably the most famous, the Parker square. Take a look at this. If we add up the rows and columns and one diagonal, we find the same number, but the other diagonal is not the same. And on top of that, it has repeating entries. If we go a bit further into the integers, we can find one square like this with distinct entries. And once again, all of the rows, all of the columns, and one diagonal add up to the same number, but the other diagonal is not the same, unfortunately. If we allow for some non-square entries, like in this square, well then, we can find a good solution. But again, some of the entries are not integer squares. Another example is a near miss that is featured in one of the number file videos, and it is that one. I don't want to show you all of these numbers, but if we sum the middle row and the middle column and both diagonals, they add up to the same number, but the other sums are different. We could obtain such kind of result where all of the sums are just a bit different if we take the digits of square roots. So let's take a look at this magic square and let's transform it into a magic square of perfect squares. So of course we have to write squares, and then some of them simplify, of course. We add digits to them, so basically we add zeros, and here is the final result. Despite all the sums are almost the same, they're not exactly the same. So the problem is still unsolved. So let's try and get into the parametrization of the problem. Find parameters that define it. And we come back to the initial definition, like so. And right after that, we can come to a basic property of that. That is, if we take as a reference the central entry, e squared, then all of the other entries can be written like so, with n and m integers. Now, I'd like to show you exactly this, but seen from another angle. And for that, I would like to consider that n and m are positive. And on top of that, just for this slide, that n is greater than 2m. We can later drop that condition, but just for the vision, that will help. So again, If we take the central entry as a reference, then all of the other ones are placed that way. And if you go a bit deeper into the numbers, you can notice that m very often appears as a difference between the entries, and sometimes n minus 2m. Now, if we put all of that together, n is also the difference between e squared and I squared and between a squared and e squared. But does such number exist? The difference between two squares from which one is common two times. Sure it does. It's called a congruum. For example, 24 is a congruum. It's the difference between the square of 7 and the square of 5, and at the same time, the square of 5 and the square of 1. You can notice that 24 could be written like this. And why I put it that way? Because any congruum, which I will call M because M is also a congruum, can be written as 4 times A times B multiplied by A squared minus B squared, where A and B are integers. It turns out that the three squares can be written like so, and every time you can check that M is the difference between them. However, we're not looking for a simple congruum. We're looking for a triple congruum. That means M should be written with these parameters, A, B, C, D, and F, where A, C, and F are in order like this, and A and B, C and D, and E and F as well. Does such number exist? Yes, it does. For example, if we take A, B, C, D, E, F as 3, 7, 5, 7, 7, 8, then we find M equals 3,360, and all the squares are written like this. Now you might notice some problem right there, because the two middle ones are not in the correct order. However, I give you another example where we take A, B, C, D, E, F as 7, 37, 33, 37, 37, 40. Then M is this number, and the squares are this time in the right order. Now, you might notice there's still something wrong, because the differences are not the same between one row and the other. Let's take a little deeper look at that. So again, M is defined like so, with the parameters A, B, C, D, E, F. And now N should be also a congruum, and a congruum defined by these numbers. So that means if we write a little simpler by dropping the constant 4, we have to find numbers A, B, C, D, E, F. Verifying these equations, and such that n, written like so, is well defined. So that means the number r, which we could call a remainder, equals 0. Does such number exist? Let's take a look. So, as an example, I would like to show you all of the possibilities where A, B, C, D, and F are positive and below 1000. You can see there's a lot, and it turns out there seems to be an infinite number of them, even though I cannot prove it. And in my search, I have looked for every number below 20,000, such that A times B squared minus A squared equal similar expression with C, D, and E, F. And then defining R, the remainder like this, actually is always not 0. So I'd like to propose a more advanced parametrization. And let's get in there. Taking again the equation like before, a bit more simplified, dropping the constant 4, we have these three equations, and the remainder is defined like so. Now, if we see that a little bit differently, and imagine that A, B, C, D, E, F are polynomials, then we can also define the remainder polynomial. Now let's imagine that this remainder polynomial is written like so, with the degree eta, and imagine we find a rational root p over q, which we can also write that way. Then all we have to do is to multiply by q to the power of eta, and then everything will be integer. Perhaps there will be common factors, but everything will be integer, and then we would find the solution to our problem. Because we could reconstruct the square using these formulas. And in that case, of course, all of the rows, all of the columns, and both diagonals would add up to the same number. I would like to restrict a little bit the polynomial parametrization to polynomials of degree 2, which means A, B, C, D, and F would be all of degree 2. If we want to look for such polynomials, we would have to check this equation for A, B, C, and D, and similar expression for E and F. I will not go into the details of solving such equations, but it turns out that it could work. However, I would like to restrict again the problem to a given A0, B0, C0, D0, E0, F0, and I will call that a seed. So from now on, a seed will be a given set. For example, 3, 88, 13, 55, 40, 51 could be a seed. Unfortunately, for that specific seed, I could not find any polynomial of degree 2 for A, B, C, D, and F. However, if we take this example, 1, 15, 2, 12, 4, 10, then here are some polynomials that could be found. It turns out that every time I tried, I could find an infinite number of polynomials. Though, again, I cannot prove it. Now, within my research, I have looked at reasonable numbers for every seed below 1000, where all the numbers are below 1000. So every time the remainder polynomial had no rational root. Now, as I announced in the beginning, I would like to focus onto a specific example, and that one is based on the seed 3, 77, 4, 70, 30, 44, which we could mirror a bit and write a little bit differently, like so. And actually, we can take the example of A, B, C, D, and F polynomials, like so. You can see on the right, the constant term is exactly the seed, as I mentioned. Now, we could also mirror those polynomials, like so, and they are still a solution to the equations mentioned above. In that case, the remainder can be written like so, and it turns out we can divide all of the coefficients by 12 to find this remainder polynomial. I put it back up here, and I would like to mention that this polynomial has 4 real roots, which you can see here. They're not rational, unfortunately, and I'd like to focus on that one. So to do so, I give here a few more digits of that real root, and written that way, we can decompose it into a continuous fraction. That means we can write this root rho as 1 over 7 plus 1 over 2 plus 1 over 3, and so on, going indefinitely. And I'd like to write this a bit more simpler, like so. And you can notice for that specific real number, we have one of the coefficients above 1000, which is pretty high. So we can take an approximation of this root, and if we take any, we can reconstruct the magic square like so. And of course, we will find the sum of all rows, all columns, and one diagonal add up to one number. But let's see what we get for the other diagonal. For example, if we take the simplest approximation, that is p over q equals 0 over 1, guess what? We find this square exactly the same as I showed in the beginning, which of course doesn't work. And as you can notice, the second diagonal is quite far away from the first one. If we go a bit deeper and take the approximation 155 divided by 1152, then we find this square from which all of the columns, all of the rows, and one diagonal add up to the same number again, but the other diagonal is slightly different. Now, as you remember, I mentioned there is a coefficient 1000 in the continuous fraction. So if we restrict the approximation just before that, then we find P over Q equals 923 divided by 6860, which is this number actually really close to the root of the polynomial. In that case, we find these raw numbers to reconstruct the square. As you can notice, one of them is negative, but that's not a problem because we're going to square it and it is the smallest of them. You can also notice that 2 is the common factor between all of those. So if we simplify everything, we get this very square from which all of the columns, all of the rows, and one diagonal add up to the same number. But the other diagonal is slightly different. As you can notice, the relative difference is below a billionth. And if we go further into the continuous fraction, the relative difference will be smaller and smaller. However, we cannot get better than about 28% of the digits. So in the future, I am quite sure that a solution can be found. But to do that, even though the search I exposed so far is quite refined, so to say, we could refine it even more. And to do so, I would like to consider the work of Hedju and others about polynomials of, let's take here a given degree. So for example, when A, B, C, D, and F are all of degree 2, our remainder is of degree 8. If we take a given degree and we want polynomials with only rational roots, then they are more likely, if their coefficients are in absolute value as high as possible, all divisible by 2 or 3, and by extension, all divisible by a given set of prime numbers. And again, by extension, if our polynomial may have one rational root, we can also take these criteria. So, if anyone wants to search, here are some examples of promising seeds. I give you here 5 examples where some numbers are greater than 1000 because they were out of the scope of my research. If you're looking for the code, it is in the description. In the meantime, thank you very much for watching and see you next time.